Okay, hopefully it's recording. All right. Okay. Hi guys. Welcome back. So we finished mechanics last week. So last week we did what did we did? We did two body interactions. So that's the final part of mechanics for this physics Olympiad preparation. Lecture series. The so just to give a sneak peek, the rest is gonna be electromagnetism, thermodynamics, relativity, and other stuff. So we've covered mechanics in like 4 weeks or 5 weeks, maybe six, and we're gonna cover the rest in like 4 or 5 weeks, which is impossible. Uh, so just to see the impossible task I am tasked of. So I am supposed to teach all of electromagnetism in 2 hours, starting from electric fields to magnetic fields to Lorentz forces to induction, linear response, and electromagnetic wave. Let me just say that this is impossible. uh, so yes, I'm not gonna do this. I'm just gonna go to talk about stuff that I find important, and maybe you do too. And we'll see how far we go. Uh, yeah, let's just see how far we go. Okay, so let's no further ado. Without further ado, let's start. Okay, so I'm really not sure about who are the people taking this lecture series. So I'm just gonna start with the basics. So I'm gonna talk about mostly today, uh, given the time constraints, is electrostatics and magnetostatics. Mm, but we will slowly build up most of electrostatics and magnetostatics. So basically, this is the static part of electromagnetism when um, most things are in a steady state. We will quickly see that this breaks down very very fast, and then and we are forced in the end to think about electrodynamics. Okay, uh, and this is just thinking about the electric and magnetic fields. We of course knows that the electric field and magnetic fields exist, and they also cr- uh, they it, they exist because of currents and charges, which source these electric and magnetic fields. But in turn, they also tell how does the current and charges supposed to behave? How do they manipulate or move the charges, and how do they change the strength of the currents? So this is a very intricate process, and like to really know electromagnetism, we need to understand this entire thing as a whole. But that's too ambitious, especially for this lecture series. So let's just start with electrostatics. So I hope at this point, most of you know about Coulomb's law. So Coulomb's law is just saying what is the electric field, or maybe I think, yeah, okay, yeah, yeah, electric field. Let's just say electric field from a point charge is basically given by. So here's a point charge with charge q, and if I look at the point, okay, a distance r away, this creates a electric field that is in the direction uh, away from the point charge, with the electric field being uh, okay, being this. So there are a few things to note about this. So the electric field, okay, this is electric field. There's a proportionality constant, which is 1/4 pi epsilon naught. Uh, so sometimes you say this is k, okay, but basically it's just a proportionality constant. It's proportional to the magnitude and the sign of the electric charge. So if this is a negative charge, there's a minus sign that's also here. and it points away from the charge. So if it's a negative charge, then the minus sign causes it to let the electric field be uh, let the magnetic field be let the electric field points towards the charge. Okay, and another important thing is that this scales as 1 over r squared. So just like gravity, the gravitational field scales as 1 over r squared. So it obeys some inverse square laws. Okay, basically that basically that it decays uh, as 1 over r squared away from the point charge. Okay, and the force, electrostatic force, is basically given by F equals to uh, Q E for charge Q. Okay, so if I have a charge Q, it will experience a electrostatic force proportional to the electric field at its position, and the magnitude is also modulated by how large the charge is. So if I have and so this, then uh, if uh, if Q is positive, the force is parallel to the electric field. Okay, so if the electric field points towards here, and I have a charge here, it will go wherever the electric field points. And if Q is negative, then F is anti-parallel to the electric field. So if I have a negative charge Q, and the electric field points here, then the charge will get a force that's opposite to it. This is the high level way of thinking about like charges repel and the opposite charges attract. Okay, so that's most of the things that you already know. So that's just a recap. But what's the important thing right now is to try to understand, okay, what happens if I have what happens to if I want to have a generic understanding about the electric field created by many charges, for example. Okay. Another important thing that we need to know is that there's superposition. So the electric field produced by many charges, okay, Q1, Q2, Q3, Q4, Qn, and all of this, creates some electric field over here at the point X. Okay, so the important thing to know is that the electric field at point X is a sum of all the possible I equals to 1 to n of all the electric field of all the created by all the charges. You just simply add up together vectorially, okay, and that's how you get things. Okay, so this is the basics of electrostatics, and I'm sure you all are very familiar. Okay, now the one thing to know is that the electric charge is quite a cool thing, that that the electric field scales as 1 over r squared. So this brings in something that's very peculiar, is that it obeys something called Gauss's law. Okay, what it means that Gauss's law is basically just an inverse. It's just because of the inverse square law. So in 3 dimensions, if I the most symmetric thing I can draw is a ball, okay, and the area of the ball of the sphere is equals to 4 pi r squared. Okay, this is interesting. Okay, so if I have because of the electric field or the electrostatic force, it decays as 1 over r squared, but the area of a ball increases 4 pi r squared, we have something that's like something like a conservation law, that if I integrate over uh, if I integrate over so if I have a surface, so random surface, and and at each point on the surface there's an area vector, okay, that points, uh normally to the area, okay, and if I have some charges, you know inside of it, and I have, some charges outside of it, and I'm gonna ask, okay, what's the sum of so and all the charges emanate some electric field. Okay, all of them have some electric field. And if I take the dot product of the electric field at some point on the surface, okay, so if this is theta, E dot dA equals to E cosine theta dA, okay. If I take the dot product of the electric field all around the surface with the area, this is a conserved quantity, that's equals to Q enclosed divided by epsilon naught, where Q enclosed is the total charge enclosed in the surface. Let's call this surface M. Okay. So if I sum over all the dot products of the electric field across the entire area, this is a conserved quantity that it doesn't matter what the surface is. It's always going to be a conserved quantity about the amount of charges that is in the that's in the surface. Okay, and so for these guys are outside of the surface. They never contribute to this quantity E dot dA integrated over. The only thing that uh, is here is the Q over enclosed. And this is interesting because it doesn't matter if your surface looks like this or your surface look like this, or your surface look like, or your surface look like, just very thinly, just closing over all the small charges. It doesn't matter. If I calculate E dot dA over, the this guy equals to E dot dA over the green guy equals to E dot dA over the black guy. All of these are the same. Okay, doesn't matter what the surface is. This is always going to be a conserved quantity, which is very important. Well, it's very nice to use because this can allow us to get electric fields over surfaces. That's just not a point. You can take the electric field over surfaces, and this is, I think, is quite interesting. Uh, and this guy over here has a name. This is called the electric flux. Okay. Excuse me. So this is electric flux. It is defined over is the integral of electric field over an area. Okay, so this is what we call the electric flux, and it's a somewhat of a conserved quantity if you change the surface, whatever surface you change. If it's a closed surface, as long as you encapsulate the same amount of charges, the electric flux will always be the same. Okay, so this is an interesting thing. Okay, what's more helpful about it is that we can use it to find find electric fields of objects. Okay, So think about a not a point charge, but a ball, and this ball has a total charge q. And I want to ask, okay, what's the electric field at some point r away from the center of the ball? Okay. Uh, Basically, you can use Gauss's law, saying that okay, E dot dA is equals to q enclosed divided by epsilon naught. And so here's the algorithm. The algorithm is that okay, the first thing you need to do is to choose a surface with symmetry. So for example, if I want to find the electric field here uh, at this point over here, you can, like, this is a ball, and this entire thing has spherical symmetry. So I know that this point is the same as asking, what's the this is the same as asking what is the electric field. Okay, there's some same r over here. This is the exact same question. Because it has spherical symmetry, it doesn't really matter where I choose this x, as long as it, the same distance away, it should be the same. Okay, it doesn't really matter where I put this. Okay, as long as the distance r. Okay, that means that there's a spherical surface. There's a spherical surface of radius r, where my initial point lie on, and all of this point on the sphere should have the same electric field because of the symmetry. And then I can use Gauss's law. So okay, so let me draw this. So this is a ball of charge q, and I want to find the electric field at this point. I can just choose this ball of this ball of mass this ball of radius r, this sphere of radius r, and then every point here would have the same electric field, and this will always point outwards from the symmetry. Okay, so since it will always point outwards, E dot dA is just equals to EDA. So the left hand side of Gauss's law just becomes summing over the area of the sphere of EDA, which is equals to 4 pi r squared. Okay, and again, this electric field points outwards, so it's a radial electric field, and this will be equals to the enclosed charge, which is this q, divided by epsilon 0, which is just a number. Okay, so we have the electric field to be q divided by 4 pi epsilon naught r squared in the radial direction for a ball of charge q. Okay, it doesn't really matter what this ball what this ball is, as long as like how big as the ball is, as long as I'm far away from the ball, this is the electric field of the ball. Okay, are there any questions about Gauss's law and its explication for now? Okay, okay. Well, most of the time we can just stop and move to the next example, but I want to stop and ponder about this a little bit, because like the reason we can do this calculation very easily is because there's some symmetry in the system. In this case, it's spherical symmetry, and I sort of gloss over. I kind of just say that spherical symmetry. So the electric field is always proportional, like it's always pointing radially away, so it's always perpendicular to the spherical surface. We can think about other possibilities, and this is a lesson about symmetry, right? So so if I think about spherical coordinates, I can have something in the radial direction. I can also have something in the theta direction and something in the phi direction, right? So for example, here, instead of the radial direction, I could have something that's pointing here in the theta direction, or I could have something that's pointing, inwards to the page in the phi direction. So, based on symmetry alone, can anyone tell me why there shouldn't be any electric field along the theta direction, the phi direction? So a lot of electrostatic questions can be solved using Gauss's law, using whatever law I'm going to introduce. But everything's going to be very much simpler if you have an understanding about the symmetries. Okay, so anyone have an idea? So in spherical coordinates, I have three independent vectors, like the radial direction, the polar direction, the azimuthal direction. Like, why is the electric field of a spherical symmetric object only in the radial direction? No, there's no form. This is nothing to do with formula. So this is a vector E. So this vector E is something that's ER in the R direction plus E phi in the phi direction, and plus E theta in the theta direction. It doesn't really has anything to say about the direction. I just said that because of spherical symmetry, the the vector is always in the radial direction. So E dot dA is equals to E dA. But that's why is that supposed to be the case? Because in this case, dA is dAr. But if I have e to the phi, then phi dot r. Well, in this case, it doesn't really matter. But yeah, but yeah, in this case, we only get the er component. But that means that maybe we need to have something that's plus phi that we didn't get from Gauss's law. Okay. Uh, so this is important, right? So why is this the case? Well, sorry, let's just. The reason is okay. A spherical symmetry is because okay. Let's just think about it. So if this guy, if I have a spherical symmetric object, okay, and this is given by a point here, a ball, which is spherical symmetric. If I have something that's in the theta direction, what does that mean? It means that okay, if because it's spherical symmetric, uh, so for example, if something that's have like a theta direction like this, I can look at it. Uh, how do I say this? So for example, if this looks something like this, if the electric field looks something like this, that has some theta direction that looks something like this, for example. Okay, suppose that the electric field has some theta component like this. If I because it's spherical symmetric, I can turn, so I can look at it in this direction. I can also look at this ball from the back, right? Okay, I can also look at the ball from the back, but this theta direction that's going clockwise will look from the back observer. So this back observer here in the back, what he will see, is that the electric field goes this way. From the same ball of charge, but the same ball of but if but the same ball of charge, but the same ball of charge shouldn't, okay, it has spherical symmetry. The ball of charge doesn't have a front and the back, but if I have a theta, like an electric field that moves like theta, an observer from the back can differentiate between the back of the ball and the front of the ball, because in one case, the electric field is moving clockwise, and in the other case, the electric field is moving counterclockwise. Okay, so surely this cannot be the case because the ball is the same in the front and the back because of spherical symmetry, and this is not spherically symmetric. Okay. Similarly, you can say that okay, maybe let's not do that. maybe we can think of something that's not completely like this. We can think about something that's the electric field can be something like this, okay, in the theta direction, but having two similar things, okay. But that means like, okay, if I have an observer like this, it looks like this. If I observer looking from the back side, okay, it will see it. So in the front side, we will see the theta directions, the electric field point in theta direction pointing towards me. But for the back observer, okay, it will look like the electric field is pointing away from it. Okay. Okay. Right. So again, this is not spherically symmetric, because then you can know what's the left side of what's the front side of the ball, and uh, what's the back side of the ball. So this is again not spherically symmetric. So the ball can never have so the electric field can never have a theta component in the electric field. Okay, so E of theta must be equal to 0. Okay, this is the same thing for the phi component. So if I have an electric charge, okay, and I have a spherical surface, and if this has a phi component, you can argue in the same way that for the electric field to have a phi component, then a guy from the top and a guy from the bottom of the ball can see it like different, like the electric field oriented different way, one clockwise and one counterclockwise, and then this is again not spherically symmetric. Okay, so basically E of phi must also be 0. Okay, that's why we had that calculation above, that we have E dot dA gives you only the r direction of the electric field, but that's fine, because we know from spherical symmetry that the electric field must only be pointing away radially from the ball. Okay, so this is so most of electromagnetism can benefit from understanding the symmetries of the object of the system. And if you understand it well enough, you find that some of the times you don't need to do any calculations at all. So it's useful to bear this in mind. So let's have a different example. So I have a line of charge. Line of charge with charge density lambda. What this charge density means is that if this is the y direction, okay, dq dy is equals to lambda. Okay, and this is a long string of charge, so it starts from negative infinity to positive infinity, so it's infinitely long. So the question is, what is the electric field, okay, at a distance a away from the line of charge? Okay. So the question is, what is the direction of the direction of the electric field? Okay, in this case, again, this is cylindrically symmetric, so this thing should either have, it can either point towards the radial direction, it could point towards the z direction, it also points towards the phi direction. Okay, so anyone have a clue of where the electric field is pointing towards? In our direction. Okay, yeah, it can only point in our direction, because in the z direction, I can I can I can look at observers looking like this and looking like this. Okay, because this is the same line of charge. Okay, they cannot see one pointing upwards and one pointing downwards. They should all see the same thing. then we know that there cannot be a z direction. For the phi direction, it's the same, right? Because I can have, so if I can have observers looking here and observers looking here, and this points in the phi direction, one can differentiate left from right. While a line, there's no left and right of a charge, of a line of charge, so there's no phi direction. So the only thing you can do is differentiate between uh, the radial directions, okay, which is just emanating from the piece of line there, okay. So good. So the electric field can only have a radial direction, and now we want to find, the electric field at the point x over here. Remember, the algorithm is to find a surface with symmetry. Now we know that it's in the r direction. We know that our surface that we need to choose must always have area vector that pointing towards the r direction. So what can we think of is a cylinder, okay, a cylinder, this, which always has an area pointing towards the r direction. Okay, and the electric field we know is always in the r direction, right? So again, E dot dA goes to E dot dA in the r direction is ER dA. So second, use Gauss's law. Now we know that, E dot dA across the entire surface is equals to EDA, ERDA of this surface. And the surface has an area of, so this is a cylinder with a radius of A, with a radius of A. And for simplicity, let us choose that this height is of length L, okay? So the area of the cylinder is ER, which is a constant because of symmetry, and 2 pi AL. And this must be equal to the enclosed charge by epsilon 0. And the charge enclosed in this spherical surface is this part over here. And the total charge enclosed, because this is a charge density, so the total enclosed charge must be equal to charge density, integrated over, integrated over, the length that is enclosed. So this is lambda L. And so ER 2 pi AL must be equal to lambda L divided by epsilon naught. So the electric field of a line charge is equal to lambda divided by 2 pi A epsilon naught, again in the radial direction. Okay, so this is how to use Gauss's law to solve problems, right? So I think it's nice to practice symmetries when we do electrostatics. So here is a question for you to think about for 5 minutes, perhaps. Suppose I have a room, which is a box room. Okay, and there's a charge Q sitting in one of the corners. Okay, so a question I want to ask is, okay, what is the electric flux? Okay, so this is not the electric charge, this is electric flux. So it's E dot dA over this entire the ceiling. Okay, so this room has a side length of A. Okay, so what is the electric flux from the ceiling of this electric charge? Okay, maybe I'll give you like 3 to 5 minutes to think. If you have any clues on how to do this. All right. So I'll let you think for 5 minutes on how would you approach this problem. Again, symmetries is your friend. Okay. Think about it. Right. So a reminder of Gauss's law. You might need to use this. Okay. And remember, this is independent of whatever surface it is. Okay. So Okay, hi guys. Oops. Okay. Let's see how. Okay, wait a minute. Has anyone gotten the answer? Okay, what's your answer? Q over 16 epsilon. Okay, yeah, I think that's most likely correct. Let's see. Not sure. Uh, well, the answer is pretty simple, right? So based on symmetry, we know that this is independent of the surface. So what can we do? Is we can take the same box, all right, and stack uh, 8 of them together to make a big box. Okay, and in the middle of this box, then is this nice Q over here, and this and we can use Gauss's law over the entire surface of the box. Okay, and this will be so this big box. Okay, this big box will be equal to Q over epsilon 0. All right. Uh, and we want to only know, what's the flux, what's the electric flux over one of this surface. But because of symmetry, we can rotate this box, like a Rubik's cube. We can, turn it like this and like this. It doesn't matter. Like turn the cube. Because the cube always sits in the center and everything has nice symmetry. We know that this should be the same as the electric flux here, 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 and across all the faces. All right. So there's uh, four small spaces in one large face, and there are 6 faces in general times 4 small faces is 24. Okay, so E dot dA of this of the small box, okay, is equals to just Q divided by epsilon is times 1 over 24. So it's Q divided by 24 epsilon 0. This is the electric flux across that. Okay. Again, so a lot of electrostatics question may seem quite arbitrary, and if what some of you might try to do this very nasty integral if you just E dot dA. Okay. But most of the time, if you try to exploit the symmetries, you'll find that the questions become way easier, as you can tell. So I'm gonna do an example where uh, where this also show. Okay, let's see. I'm gonna do an example. So this example is basically saying that, okay, if I have a charge sheet of charge density sigma. So sigma is a area charge density. So is equals to dq over dA. All right. So the question is, so let's say that this has a side length of a, and then in the middle, like, okay, at a height a over 2 above the sheet, what is the electric field here? Okay, what's the electric field here? All right. Um, First of all, from symmetry, you know that because of the symmetry's system, the electric field can only have a z direction, so it can only points up. Uh, and if you really want to do this, well, the way that the traditional way of doing this is that, okay, I can specify an area here of small charge dq, and this charge will give an electric field this direction. Okay, and then I'm just gonna sum over all this charge, all this electric field, and then Um, and then you will find that you'll find the total electric field. So electric field, okay, is we know is in the z direction. Okay, so let's just sum over the total area. So the electric field is sum over small electric fields. So sum over small electric fields, which is basically dq divided by r squared, uh, right? But because this has a cosine theta, or a uh, so let's just be z. So a cosine theta, uh, and dq again is equal to sigma uh, sigma dA, and dA is basically equals to, let's call this the x direction and call this the y direction. Then we have from the x direction is negative a divided by 2 to positive a divided by 2, negative a, so this is dx, negative a divided by 2, a divided by 2 of dy, and then we have sigma uh, uh, dx dy from dA, and then r cubed is basically x squared plus y squared. This this distance is basically x squared plus y squared, and then plus z squared to the 2/3, and then there's a z from the z there. So this is how you calculate the entire thing. Okay, I'm gonna spare you the details, but I'm gonna tell you that this is correct. So I'm gonna let you. So I'm gonna give you some of the integrals to do on your worksheet. Okay, but if you believe me, what this integral is in the very end is basically sigma divided by pi epsilon 0. Sorry, there's gonna be sorry, let's say 4 pi epsilon 0 here from the constant proportionality. Okay, 4 pi epsilon naught. Okay, so sigma divided by pi epsilon 0, arctangent of z is basically L divided by 2, divided by 3 L divided by 2 squared. Okay, and this is basically, so this is for you to check your home that I haven't bluffed, and this is actually, the brute force value of the integral, and this is basically 1 over square root of 3. Okay, does anyone know what is 1 over arctangent of 1 over square root of 3? This is homework. Okay, so if you don't, this is 60 degrees. Okay, or basically is pi, sorry, 30 degrees, or is pi over 6. And what you get is that the electric field this is 6 sigma divided by 6 epsilon naught. At this point, okay, you might think that, okay, this looks very similar to what was the result over here. Right, the electric field that we have is basically, so remember for this question that we have a charge over here, and what is the flux from the at the ceiling, we have the flux is equals to q divided by 24 epsilon 0. Or if I find the electric field, or the mean electric field across, so let's say this is divided by a squared. This is something like, q divided by, the area 24 epsilon 0. Okay, so that's something like a charge density over here. Okay, that has almost the same, uh, denominator. Okay, so what's happening, right? So again, there's a question of symmetry over here, and this time the symmetry is not of the system, but the symmetry is of, of Newton's law. Okay, so when I ask, what is the electric field of this thing at this point over here, okay, the electric field is basically, you know, uh, just dq over 4 pi epsilon naught r squared. Okay, so if I have a charge q over here, then it will experience a force that is q dq over 4 pi epsilon naught r squared. Okay, this is the force going to be experienced by this charge over here. But because of Newton's third law, you know that, okay, the entirety of this square also experiences a force, which is of the same magnitude, but in the opposite direction. Um, and this is pretty cool. So now we don't actually need to calculate the electric field at this point, okay, from the entire plate. But what we can do is to ask, okay, uh, what is the force per unit charge, okay? So the force per unit charge is basically the electric field, okay? The force per unit charge of this Q over this entire surface, or basically what is the magnetic what is the electric flux divided by L squared uh, at the bottom of the chart, at the plate, right? At the plate, and we know how to do this, right? It's the same way as we did. This is L over this is L, and this is L over 2. What I can do is you can also place a plate here, place a plate here, place a plate here, and also in the front and the back. And then we know that the electric flux is given by the total electric flux is of this entire cube is basically Q over epsilon 0. So the electric flux and this place is basically equals to 1/6 of the charge. It's yeah, and no, okay, and then the electric field is basically this thing, which is basically sigma by q epsilon naught electric field. Okay. All right. So there's this. I've gone through this very hand wavily, but okay. This is another symmetry that we can exploit when we do electrostatics. And I will, this is done very hand wavily, so I'll give you a little bit more rigor in the worksheet. But again, like electrostatics is all about symmetries and exploiting all the symmetry you can about the system, about the geometry, and about like Newton's law. You can find that electrostatics can be quite easy to work with, and most of the time you don't need to do these very difficult integrals, but you're welcome to do them. All right. Any questions about symmetries and electrostatics? All right. If there are no questions, all right, let me move on to magnetostatics. So, electrostatics is about electric fields caused by electric charges, and magnetostatics is about magnetic fields caused by static currents. Basically, something like uh, a something like an electric current that's like dq over dt. What's the rate of charge that's passing through a point? Okay. So what is what is the current? The current is basically the rate of so I is defined at some point x. Okay. So basically electric current is basically the rate of charges passing through a point x. Okay, so this is what a current is. Most of the time when we talk about currents, we think of currents in a conductor. Okay, so for example, like a wire. Okay, and where the total net charge is zero. Okay, so there's the same amount of positive charge and negative charge in the wire, and there's a and only some of the charges move. Uh, okay, and like the negative charge move, but the total charge is zero, so that there's no electric field, but there's going to be a magnetic field. I'm going to talk about the magnetic field later. So this is an important thing. So if I just have a stream of negative charges and all of them are moving with some velocity v, okay, okay, and I can ask, okay, at this point x, there are going to be charges moving through this point x, okay, right? There's going to be charges moving through. What is so in this case, there's going to be a magnetic field, but also there's going to be an electric field because this is not a neutral system. This is literally just a charge of a stream of moving electrons. So uh, this has an electric field associated to it. This is a misconception that people usually forget forget about when they talk about currents. So they say that, okay, currents don't have any electric field; they only have magnetic fields. That's not correct. That's only correct if you have the same amount of charges in the current. That's like, okay, in the system there's the same amount of positive and negative charges, such that there's no net charge, so there's no electric field. But if you just have a stream of electrons or stream of protons, that's not necessarily true, and this will actually give off a considerable amount of electric field. All right, so this is a misconception I was trying to clear out at the very beginning. So so yeah, so we talked about the current as a rate of the rate at which charges passing through a point x. But we can think about, at sometimes, what we can do is we can put some voltage over here, and maybe ground a bar over here, and then in the middle, uh, for example, this may be two banks of a river, and then I ground the river here, and then I have some some charge plate over here, and the river conducts electricity, and there's going to be a moving current over here. In this case, the current is not over a point x. It's the current passes through some line over here. Okay, so in this case we define a surface density, a current density. Okay, what we talk about is look at some area over here, and we ask, okay, what is the current moving through this area? All right, so basically instead of so the charge, what we see is that the charge moving how can I say this? Okay, the current, instead we define the current density, which is which is a density k. Okay, the current density k, and the total amount of charge passing through per unit time. Okay, is k. Well, is k is k dA. Okay, it's k dA. Right. Also, sometimes instead of that, we have a very large piece of wire. Okay, which has a non-negligible surface area. In this case, we also have things that passes through. The current passes through not just a surface but entire volume. In this case, the current density is usually, so this is a disk of dV, of volume dV. So the current density is called J, and the amount of charge passing through is basically J dV. Okay. So these things have some directions. Okay. So these currents have a direction associated to them because it's not just a point anymore where you can only go through a point uh, in a specific way through a line. Okay. So if you have a line, it's perfectly defined how you get to a point. But if it's a surface, then the current density then carries some direction that you need to specify. All right. So these are currents, and as I just said, currents generate magnetic fields, and this is given by Biot-Savas law. So magnetic field generated by currents is given by Biot-Savas law, which is B is equals to mu naught divided by 4 pi. This mu naught is 4 pi times 10 to the minus 7 in SI units. I think that is true, or maybe it's 10 to the 10 9. Yeah. Let me look it up. Yeah, it's 4 times 10 to the minus 10. If you want SI units, this is H over M. Okay, mu naught. Okay. And integrate J. So in the most generic case for volume currents is a JdV cross R divided by R squared. So this is Biot-Savas law. You can substitute this JdV in terms of kdA for a surface current, or I ds, where ds is the line, like the line of which the current passes through for a line current. All right, and this is Biot-Savas law, and this is how a current basically generates a magnetic field. All right, so let's just go do this by example. So in this case, we have a current of I, right, moving in this direction from negative infinity to infinity. Okay, and we want to see, okay, what is the magnetic field at this point x at a distance a away. Okay, all right. So here's a question. Yeah. So maybe I should tell you what these symbols mean. JdV basically just tells you, like integrate over the entire current, and then this R is so this is the so if this is I have a surface current going here, surface current J, okay, going around here, and I'm asking at some point away from this point, okay, this R is basically like considering JdV over here. What is this? And this what this distance is basically R, and the position vector pointing to the point is basically R hat. Okay, so the question is, okay, now given a wire, what is this what is this what is this magnetic field at a point at a radius a away from this wire? Okay, so again, electromagnetism is a question about symmetry. Is mostly a lot about symmetries. So we can know that this has three directions that it could go. The directions could be r, it could be in the z direction, or it could be in the phi direction for the magnetic field. Does anyone have an idea, like what is the direction of the magnetic field? based on symmetries, just based on symmetries, where what can in which direction can the magnetic field point? Phi. Why? Is there a reason why phi? Why can't it be something else? This is I personally think this is a really interesting question, right? Uh, yeah, it's the cross product of the position and the current direction, right? But can you argue by symmetry that it must be in the phi direction? This is a bit more difficult, as I found. Uh, so in this case, is there are less symmetries to exploit, but we know that, okay. First of all, yeah, from symmetries, like how can you know that it can't be in the z direction or the r direction, right? Okay, never mind. This is an interesting question that I think we can think about. I thought about something, but now I can't think about it. But yeah, let's just forget about symmetry for now, and then I'll come back to symmetry maybe a little bit later. The right hand rule is symmetrical. I don't think that's the answer. Uh, but it's a good question to ask. Okay, I'll go to the example later where the symmetry is a little bit more apparent, and then you can actually, maybe in this case it's completely fixed by the cross product. Okay, so the cross product says that the direction of r is in this direction, all right, and the current flows in the z direction, all right. So uh so what happens is that you can only get it. So for z cross r, right? You can't get DNR anymore. So the only possible direction of where the magnetic field is in the phi direction. Okay. Uh, yeah. So what we can do is we can now calculate. Uh, so B of phi. Okay. We'll come back to symmetries later. I'll give a better answer about symmetries. In this case, this is a constant current, so you can take it out. ds is dz in that direction, and then it's divided by r squared, which is basically a squared. Sorry, that's not true. What we are thinking about is, this current element here, which is I dx, sorry, I dz. And then the r squared is basically this r squared over here. Yeah, so yeah, so it wasn't true. This was this r this r was, it can be in the z direction and can be the r direction, but nevertheless it can only go in the phi direction. um so basically, yeah, so the length is basically z squared plus a squared. Okay, it's basically z squared plus a squared. uh okay, sorry, let's do this a little bit more proper. Okay, so this is uh yeah, so this is the r direction, so let's call this the rho direction. Okay. uh we know that, yes, the symmetry. So some of the symmetries tell me that, okay, because of translational symmetry, I can always find in the z direction. Because of translational symmetry in the z direction, I know that I can always find something that's, opposite to this. It gives you the opposite r. Uh, and the the and r cross z gives you uh, z cross r. Okay, z cross r gives you in the phi direction. Uh, Wait, do I need to do this? Let me think about this. No, I don't need to do. I don't need to do this. Okay, let me think. Yeah, yeah. Okay, so r. Sorry, let me be a little bit more methodical. Okay, r always lies in the rho z plane. So it's always perpendicular. Okay, it's not always perpendicular, but it's so b is always in. It's always perpendicular to rho z plane. So there's only a b phi component. Okay, so b can only be phi. All right, but there's gonna be a modulation from the cross product from r cross, from z cross r. All right, so this, remember that this is z. Okay, so z cross r will always give you a phi component, but it will be modulated by a sine of this of theta, where the theta angle is, this angle z of r over here, right? Or basically is 180 degrees minus this angle. Okay, is 180 degrees minus so theta. Okay, is this angle over here, which is also this angle over here. Okay, that's sine theta. So basically, okay, so if we go back and do the calculation, then we know that the phi component of the magnetic field is mu naught divided by 4 pi, the constant current I, and then because there's a dx and there's a sine theta, the sine theta is basically a divided by sine theta is a divided by hypotenuse, which is r. Remember, this is r. So r a divided by r cubed from negative infinity to infinity is equal to mu naught I divided by 4 pi, negative infinity to infinity, a dx divided by a squared plus x squared over 3 halves. All right. Then we can do some substitution that let a become a tangent of theta. Sorry, let's use some other a tangent of alpha. Dx is then a second squared of alpha, d alpha. Then we can have b phi is equals to mu naught I divided by 4 pi. Okay. A squared second squared alpha, d alpha. And then this is basically a to the third 1 plus secant squared alpha to 3 halves. And when theta is when x is negative infinity, when x is negative infinity, then tangent alpha gives you negative infinity when this is at negative pi over 2, and instead this is pi over 2 when it is at positive infinity. Okay, remember that tangent 90 degrees is equals to infinity, right? Okay, so we can now do this integral mu naught I over 4 pi. Okay, this a squared is it can be done to get a over here, negative pi over a, pi over 2, 1 plus, this is tangent squared, and 1 plus tangent square of alpha is secant squared. So this is secant cubed, so it's basically a cosine alpha d alpha. We know how to do this integral. It's basically sine alpha from pi over 2 to minus pi over 2. And basically this is just 2. So the answer is mu naught I divided by 2 pi a, or b is equals to this in the phi direction, right? Okay, so that's Biot-Savart law in action. As you see, this is a lot of work. You need to make sure that you have the cross products right. You need to make sure you have the directions right. You need to make sure you have the integrals right. And this is a lot of work to get the magnetic field for a current carrying wire. So there's gonna be a lot, as you would imagine, there's gonna be a lot of simplicity. There's going to be a lot of simplicity just by looking at the symmetries of the problem. Okay, so first of all, as we know that this is if we look back, that the Biot-Savart law is also one of R squared law. Okay, so it's an inverse square law, and inverse square law importantly has some weird conservations of laws in 3 dimensions. In particular, we have something called Ampere's law. We say that if you have just randomly some current carrying wires, okay, and if I have if I have a loop which this current pierces through, so this current pierces through these loops. All right, Ampere's law tell me that so there's going to be a magnetic field along these wires, along this loop. So this is B. This is B dot dl. All right, B dot dl is equal to mu naught by times the enclosed currents. Okay, so anything that is in this loop, all right, is enclosed. And again, this is independent of how you close these loops, how this loop is drawn. So it can be this very nice loop. It can also be, it can also be, just barely circling these oops, barely circling these current carrying wires. This is okay. It doesn't matter. It can also be, let's use a different color. Okay. So it doesn't matter if it's this way of circling the currents, or it's this way of circling currents, or this way of circling currents. It doesn't matter. However you circle the currents, that's the same thing as an Ampere's law. That no matter how the loop is done, you always have this law to hold, and this can give you a lot of simplifications when doing magnetic field calculations. Okay, so for Ampere's law, let's do an example. So we just found out that if I have a current carrying wire, at a distance a away from it, the magnetic field is equal to mu naught I divided by 2 pi a in the phi direction. Okay, now we know, okay, again, we know that this is in the phi direction. So what can we do is that we can draw a loop. Let's use the orange color one for consistency. We can draw a loop, okay, that's of radius a. And then B dot dl, we know that B is in the phi direction, and dl is along this loop. And if we chose dl to be completely circular around the phi direction, okay, then this will also be equals to B dl, which is the dl is basically a small segment of this loop, and integrating over the entire circumference, this is basically 2 pi a of b must be equal to mu naught of I enclosed, which is just I, and we can just find that b is equal to mu naught I divided by 2 pi a. Okay, without using Biot-Savart law and its complexity. Okay, let's do another example. This is of the solenoid. So a solenoid is basically, a tightly wound coil that has current passing through. Okay, so what we can do, so the question is, what is the magnetic field outside of the solenoid, and what is the magnetic field inside of the solenoid? Okay, so let's, for simplicity, let's consider, so if we have a zoom in here, basically we have, like something like current carrying coils, something like this. We can simplify this into, current coming out of the cage, very tightly wound, and current going into the page. Okay, and then what we can do, okay, is if this is very, very long, if this is a very long solenoid, okay, translational symmetry tells us that we can try to understand, okay, what is the, we can know that the current over here, the current is out, in and out of the page. Okay, if I draw it like this, is an in and out of the page. So if I have some point over here, okay, and the radius r, because of translational symmetry, we know that this guy can only have a magnetic field pointing in this direction, right? Okay, is that okay? Knowing that the magnetic field only points in the direction of the length of the solenoid. Yeah, okay. So we can do a loop along this path, something like this. Okay, and we know that b dot dl, okay, because b is only in this direction, so let's call this a b b in the rectangular. So this will be sum of b b dot a plus sum of b dot minus a, because this is in the negative direction. Sorry, this is, let's just not put sum. Plus b dot b plus b dot minus b. These two are 0 because the magnetic field points perpendicular to these points, and b dot a plus b dot minus a is 0. Okay, sorry, it might not be 0, but whatever it is, but this is equals to mu naught of I enclosed. But this current, this loop over here, okay, this loop over here does not carry any currents, so I enclosed is 0. So B is 0 outside of a solenoid, of a very, very long solenoid. This is not really true if it's a finitely long solenoid, okay, but this is definitely true for an infinitely long solenoid, just based on the symmetries, okay. You can do the similar analysis, putting a loop here, okay, Again, let's call this A, B, and B. We know that the magnetic field here is 0, so we don't need to think about this. This is 0. Okay, and then again, these magnetic field here, like anywhere inside the solenoid, uh, can only have magnetic fields that pointing in the z direction. So these two are 0 because B is pointing in the z direction, and this is 0 because B equals 0 outside from here. So the only thing that's here is basically V dot A, which is BA, must be equal to the amount of current here, which is mu naught I enclosed, and the total amount of enclosed is basically, the is basically how the number of the number of coils in A. Okay, so basically n the number. So let's call this the number density line. So n is basically number of coils per length, time the length, which is A. Okay, and times individually it carries a current of A. So we know that the inside of a solenoid have a magnetic field, which is mu naught n of I. And that's the magnetic field of a solenoid. So inside an infinitely long solenoid, outside of the infinitely long solenoid, the magnetic field is 0, and inside a solenoid it always points along the length of the solenoid with a magnetic field which is mu naught n of I. Okay, and I need to turn on the. Okay, this is not turned on, so let me wait a minute. Is this not on? Okay. All right. All right. So that's Ampere's law, and that's most of magnetostatics. So now I want to go back to a question. So just now I talked about the infinitely long wire of current I, and I told you that at a distance A away from the wire, B is mu naught I divided by 2 pi A in the phi direction. So this is for an infinitely long wire. Okay. Okay, maybe before that we should have a different question. Let's have a different question before we do. Should we have a different question? Nah, never mind. Let's continue with this. Okay, so this is for an infinitely long wire. Just from Ampere's law, right? What about a finite length wire? So the wire starts from A and ends at B, okay, and then has an I, all right. So let's just, for simplicity, consider the middle of the wire. Okay, for example, this is A, this is minus A. Okay, this is 0. Okay, so at a distance, oh, let's not use A. Let's just use X. Minus X and X. At a distance A from the wire, what is the magnetic field? Okay, so naively, you would say that, okay, this has cylindrical symmetry. So what I should do is I just have a loop, and then from the same analysis, B dot dl is equals to B dl, which is equals to, and integrating this is 2 pi A equals to mu naught and I is passing through. So B is equal to mu naught I divided by 2 pi A. All right. So this is the magnetic field of a finite length wire. Does everyone agree with this derivation? Yeah, you can use your emoji. How do you? I don't know how to use emojis here. Ah, cool. Does everyone agree with this derivation? Okay, I'll let you guys think. Does everyone agree with this derivation? So what this says is that the magnetic field of a wire does not depend on the length of the wire.
I think
Yeah, someone
I
was
think
saying.
I think this derivation is wrong.
Why?
Mm. Wait, can I have another moment to think real quick?
Anyone else? Does anyone have any opinions? You guys remember the derivation? I also derived it very explicitly using Biot-Savas law for a reason. Let's do this. Ah,
Wait, I have a question.
yes.
Wait, okay, I was gonna say, I think it's wrong because if we apply the same method, and then obviously if the length is finite, the bounds will be different, right?
Yes, that's what I'm
And
gonna
then,
say. Yeah.
oh, okay,
So for
yeah, and
example,
then,
this I can go from minus x. Let's use big X to large X. And if we did the if we did the same derivation as before, okay, we know that this will become cosine of theta, d theta. If I do remember correctly, if there's no, I think it's mu naught I for pi a, mu naught I, okay, this for pi a, and then this will be some negative theta naught and some theta naught over here. That's not pi. That's not that is not pi over 2. And then I know how to do this derivation. This is basically uh, sine of theta, uh, sine of theta naught minus sine of negative theta naught, which is 2 theta naught. Okay, but theta naught is this angle over here, which is mu naught I divided by 2 pi of a sine of theta naught. Okay, so remember, if theta naught was 90 degrees, then this is 1, and then I get my answer. But now I know that b phi is not sine of theta, not mu naught I over 2 pi a, but it's multiplied by sine theta naught. So that doesn't answer my question. Why does Ampere's law fail in this situation?
because symmetry.
No, the symmetry are there. I don't know where the symmetry is wrong. Again, the symmetry also tells me that b phi is always in the phi direction, so I can always do b dot dl. I can always do b dot dl, uh, and b dot dl because well, this is Ampere's law. I'm just using it, and b is always in the phi direction. L is always in the phi direction by the way I've drawn the loop. So b dot dl is b dl, and I can really do this integral, which is b 2 pi a, which is equals to mu naught I, which is the enclosed current. So what is wrong?
Is it because B? I mean, B is not because the way integral is done. It shows that B is constant, but B is a function of A.
No, B is not. B is
I
a
mean, not
function of
function.
A.
No, I mean like the B because the sine theta not will be dependent on how far away you are, right?
No, it's still at
If
A.
you, so you come again?
It's still at A. It's still at A. This is still B phi at A. This is still at this point.
Oh yeah, true. Oh, okay, let me think.
It's okay. It's a very subtle thing that I said very beginning of magnetostatics, is that uh it's a question about steady currents. Magnetostatics care about steady currents, basically saying that okay, the currents must be steady, and the entire system must be steady. This is not a steady system. Why is it not a steady system? Or there's some environmental issues going on. Because remember that I is equals to dq over dt, which is the rate at which charge is passing through a point. So if there's a steady current dq over dt, at the end point here and the end point there, something's happening. There's a dq over dt flowing out of this point, and a dq over dt flowing into this point. Basically, what happens is that you are accumulating charge here, and you are depleting charge here. So this is not really a steady system, because you are depleting charge at one end and accumulating charge on another end. So you can still find you can still use Biot-Savart's law, because Biot-Savart's law doesn't really care about this, but Ampere's law do care about this, because these endpoints really break the like really break this. So as I said very early on, that we are trying to gonna understand electrostatics and magnetostatics, we'll find that this is broken down very quickly, because this is not a magnetostatics question. This is really electrodynamics happening. Okay, so what happens is that we have uh, in Ampere's law, we have we have not thought about conservation of charge. So because if we just have a steady current, and like this, there is if we can't just have a steady current without a movement of charges. Okay, so every charge is every current is associated with a movement of charge. So if I have a finite wire, it depletes charge at one end and accumulates charge at the other end, and this is not included in Ampere's law. So this was found out by Maxwell by using another argument with capacitors, but I'm not going to go into that. Because capacitors is Zhizheng's job next week. But Maxwell basically found out that there's something wrong with this statement, and instead, what is actually true is that Ampere's law needs to be modified to, you still have B dot dl, you still have mu naught of I enclosed, okay, but to include the movement of charge create and the charge is giving out a change in the electric field, you have this thing over here, which is B dot dl is equals to mu naught I enclosed in this area, and also the change. So this is always associated with a surface. So in this case, instead of just the surface enclosed by so B dot dl integrated over is not just mu naught times I enclosed of the wires poking into this loop, but it also is plus this contribution, which is the amount of electric flux that is changing in this loop. And in this case, it is true that when I deplete charges over here and accumulate charges over here, right? So let's say that this has become more and more. So this gives out, this is a positive, this is a positive charge. This, this gives off electric field lines, appears as true, and gives you an electric flux. This also gives you some electric flux. But as short times go by, this becomes stronger because they accumulate more charge. This becomes weaker. This becomes weaker. Okay, so the electric flux that's passing through the surface is actually changing with time, and we need to take that into account. And this is basically Maxwell Ampere's law, which is the final actual way to do it. And if you do it correctly, using Ampere's law for a finite wire, okay, for a finite piece of wire, you can still use Ampere's Maxwell. You can use Maxwell like modified version of Ampere's law with this way. Okay, but in this case, you need to really take into account that this dq dt over here is really changing the electric flux over here, and including this into account, you will it is true that you will recover that this is that B is equals to mu naught I divided by 2 pi A sine of theta naught. So this is part of your homework. To prove this is true with Maxwell Ampere law. Okay. Any questions with this? I'm sure most of you have not thought of this in your life before. I find this one of the coolest things I ever thought about. So yeah. Okay. So we're running slightly out of time. We have 10 minutes left. I can't cover the rest of electromagnetism or any part of electromagnetism in 10 minutes. So I'm just gonna talk a little bit more about Maxwell's equation. So just now we already have two parts of Maxwell's equation, which is actually the more important part, which is Gauss's law, which is basically saying that the total integral over some surface basically is Q enclosed divided by epsilon naught. This is Gauss. We also have the next important one, which is saying if I have some loop, okay, this is some loop, this is some area, okay, so it's somewhat different. There's some loop, B dot dl, the magnetic field along this loop is basically mu naught of I enclosed plus Maxwell correction, which is epsilon naught d phi e dt. This is Maxwell Ampere. These are the two more important ones of Maxwell's equation. Why are they more important? Is because okay, never mind. It's because of reasons. But there are two more Maxwell equation. Basically, the first one is called magnetic. I'm just going to call it magnetic monopoles. So basically, it's the same as the first one. B dot dA for any magnetic field is 0 most of the time. Sorry, or for currents. So as you said, that I've said that that magnetic fields usually come from currents, but in some cases of physical Olympiads, people talk about magnetic monopoles. And for magnetic monopoles, this is modified to be proportion. Let's just say proportional to, because it depends on how things are defined. I think it's fine. Is equals to G enclosed divided by epsilon. Okay, I think it's mu naught. G enclosed for magnetic monopoles. What magnetic monopoles are is charges of magnetism. They don't occur in nature, so we have positive and negative charges of electric field lines. Of electric fields. Most of the time, when we have magnetic fields, is usually caused by currents, right? But there can also be something called magnetic monopoles, which have charge of G instead of Q. We call them G, and they give off. They are like north or the south of a magnet. Minus G, which, as we have learned before, that magnets don't have. You can't break a magnet into two. You can always either have north south, and you break it, you got north south. So you always have magnetic fields going in loops. And the thing that magnetic fields go into loops is B dot dA equal to 0. So for currents and magnets, I guess. But in theoretical physics, there are some things called magnetic monopoles, and if they're not there, this mu naught G enclosed is never 0. Don't worry about it. You can don't think it's there. You can, for as long as there's nothing, as long as the question never concerns magnetic monopoles, B dot dA is always 0. And the last one is basically E dot dl across some loop is equals to negative d phi b dt. The phi b is magnetic flux. So in this case, there's magnetic field punching towards punching out of a surface. So that's just like how the electric field was, and you can define a magnetic field, magnetic flux, the same way you did for the electric field. And this is basically Lenz's law. Faraday's law. And it basically concerns electromagnetic induction. I think Zhizheng will say more about Faraday's law next time when he talks about inductors. But we don't have time to get more into details here because I want to give you at least one more example before we end. So you can have another nice understanding about how symmetries really help you understand the electromagnetic fields. So this is a question from last year's OFM, round 3 in 2025. This year, sorry. So basically, you can think of neurons as a very long, as something with an axon, and with a very long body, and the long body here, all right. So this is also, I'm gonna give this as homework as well, but you can think about it now. Has some electric charge accumulator on it. But because this guy is in a medium, sometimes, and this is not perfectly insulating, there is going to be charge flowing out of the axon. So you have a current that is in the radial direction. Let's use rho for this. In the radial direction, okay. So the current, basically, the charges flowing out of the axon, basically flowing out of the neuron, basically is in the radial direction. So the question is, sorry. If the current density is cylindrically axisymmetric from the neuron, what is the magnetic field associated with this associated this with this electric electric current. Anyone? So let's do one last question to finish things off, because I think this is a very nice symmetry question. So the first question is, if I want to find the electric and the magnetic field here, okay, again, we have, it can go in the radial direction, it can go in the z direction, and this has cylindrical symmetry, and it can go in the phi direction. And anyone tell me, like, what direction is the magnetic field in? Anyone? Okay. I think that's.
Is it in phi?
Sorry.
Is it in phi?
Yeah. No. Let's think about it. Okay. So first of all, can it be in the can it be in the z direction, right? If this is long enough, so let's think about this neuron being like really long. Can it be in the z direction? Yeah, can it be in the z direction? Well, in this case, I think this is a very tricky question if you don't know symmetries. So the understanding is, okay, if this is really in the z direction, so you have something like this, I can flip this entire neuron like back to front, or basically you can say that, okay, I have an eye here and an eye here. Okay, if there's a magnetic field in the z direction, one eye will see it pointing towards it, the other eye will see it pointing away from it. But this neuron being like very long, it doesn't really like, you shouldn't be able to tell which is looking from the front and which from the back, because the currents are all pointing radially. Basically, this is like a wire looking like this, and you're asking, like, can you differentiate it from here and here? Because you can't, then, but if you can, so it should not have a magnetic field that points like this, because if it does, then you can differentiate it. So we know that, first of all, cannot be in the z direction. Z direction is there. The next question is, by symmetries, can it be in the phi direction, right? Well, again, the phi direction you cannot, right, because of symmetries. Because again, this is something like a stick that has, currents carrying out radially. So if you just rotate this stick, it looks axisymmetric. There's cylindrical symmetry, so you can't tell it apart. So if I have some magnetic field that's pointing like this, okay, and I over here and I over here, from two ends of the rods, can tell it apart. So it cannot be in the phi direction. This is in contrast to if I have a wire, okay. If I have a wire, it really tells me that I can that okay. So if I have a wire, and I have a magnetic field that looks like this, I can really tell it apart. I should really be able to tell it apart, because if I have an eye over here and I over here, one thing looks at the current pointing towards me, and this is going clockwise, and one is pointing away from me and it's pointing counterclockwise. So you can tell it differently because you see the current flowing in or out from you. So it's fine to have a bidirection magnetic field if you have a current carrying wire. But in this case, it's emanating radially, so you shouldn't be able to tell from the axis symmetry. So also shouldn't have a phi component. So the only component you should have is in the radial direction. But here's an interesting thing. You can do the same, thing. You're like, okay, you can put a cylinder here, just like how we did for Gauss's law. And because the magnetic field can only point outwards, but Gauss's law for magnetism says that B dot dA must be 0. So we know that. So for a radial surface like this, B rho is also 0. So in this case, there's no magnetic field at all. So there's no magnetic field for a radially emanating current. And this was a question in last year's OFM. So you need to know that, okay, this was a very, this question was, how many? 1, 2, 4. This is a 5-point question last year in OFM round 3. And it requires nothing more than understanding that, symmetries basically tells you that there couldn't be any magnetic field based on symmetries. Yeah. So this is so the lesson of the day is that symmetries are very useful. And yeah, do use it if you can. All right. So any questions before we end today's session? If not,
I think not.
Well, because E&M is not interesting. I guess.
Can I solve every problem using symmetry?
No.
I see.